ever try to picture like a box, but it's got way more than 3 dimensions. Yeah, me neither. Not until I really got into this whole random tensor thing for this deep dive.
Right.
It's wild. And we're talking about how these things play into quantum information entanglement, you know?
Yeah, pretty amazing stuff. And what we're looking at, this paper, it's called Free Cumulants and Freeness for Unitarily Invariant Random Tensors. So it gets at how random
the title.
Right. Gets at how randomness actually works in the quantum world,
Yeah.
which is already kind of a mind-bending thing to start with.
Oh, absolutely. So, okay, for our listeners who are maybe just wrapping their heads around this whole tensor idea.
Sure.
Imagine you've got a spreadsheet, right?
Right.
Rows and columns full of numbers.
Now take that idea, and instead of just rows and columns, you add layers, dimensions.
Yeah.
It's not so flat anymore.
Yeah.
That's your tensor.
Exactly.
And they're not just some theoretical math object. These things are showing up everywhere. Physics, data science, we're talking machine learning even.
Yeah, they're everywhere. And when you get to the quantum world, that's when tensors get really crazy. Because now they're not just about, organizing data. They're representing all the different ways that particles can be linked together, even if those particles are miles apart, right?
So it's not just about where they are, but how they're connected somehow.
Yeah. It's about how they kind of dance together, even across these huge distances. That's entanglement. And that's one of the weirdest and coolest things about the quantum world, I think. Absolutely. It's like they have this secret communication going on that we're just starting to tap into.
Right, exactly.
Now, this paper, it focuses on a particular type of tensor, right? Those that stay constant.
Yes.
Even when you apply certain transformations.
Right.
So help me wrap my head around this. What kind of transformations are we talking about?
So imagine like a diamond.
Oh.
You can rotate that diamond, look at it from any angle, but it's still fundamentally the same diamond, right?
Yeah.
These transformations, they're kind of like those rotations.
Okay.
We're interested in the tensors that hold steady no matter how you look at them, no matter how you transform them.
They keep their core properties.
Exactly. We call that unitary invariance.
Unitary invariance. I love the jargon, right?
Right. But it sounds more complicated than it is true.
Okay, so why is this so important? Especially when we're talking about something as mind-boggling as entanglement.
Because these transformations, they're key to understanding how information actually gets stored and shared within these entangled systems. Each tensor, you can think of it like it represents a different configuration of that information.
So if we can crack the code of these special tensors,
yes,
we could unlock some serious secrets about entanglement itself.
Precisely. And one of the tools they use in the paper to do this is something called a trace invariant.
Oh, here we go. Is it time for another analogy? Because I love those.
I know you do. Okay, so imagine you have a really complex machine.
Okay, I'm picturing it.
Lots of gears, gadgets, moving parts.
Gotcha.
Trace invariants are like the key performance indicators. They tell you how the machine is doing overall without you needing to understand every single cog and wheel.
So it's like a shortcut to understanding what's going on, cutting through all the complexity.
Exactly. You got it.
I love it.
And these trace invariants, they give us a way to measure and characterize these complex tensors.
Okay.
And here's something else that's kind of neat.
Tell me more.
They help us connect what we know about matrices, which maybe you're more familiar with.
Sure, a little friendlier, maybe.
Right. And these multidimensional tensors, which are kind of the next level up in complexity.
Okay, so we can actually use what we know about matrices to understand these crazier, higher dimensional tensors.
It's like we're climbing up the ladder of mathematical complexity. You can think of a matrix as a simplified version of a tensor, and this paper shows us how some of that math we're used to using, we can scale it up to tackle these tensors.
We're venturing into the unknown, and I have a feeling things are about to get even more complex as we keep climbing this ladder. This is why we bump into things like Gaussian scaling and, what was it again? Those melonic invariants.
You're on the right track.
Okay, good.
Gaussian scaling is kind of like a benchmark. Helps us compare different types of random tensors, how wild they are, how much they fluctuate.
Got it.
And you're right, that's where these melonic invariants could come into play.
Okay, before we go any further, you have to explain that name to me. Melonic invariance. Sounds more like something you'd find at a candy shop than in a physics equation.
That's a funny name, I know.
Yeah.
But they have a huge G impact on how these random tensors actually behave.
Okay.
Especially when it comes to, you guessed it, entanglement.
Of course. So if we can nail down these melonic invariants, we get a much clearer picture of how these complex, entangled systems work.
Exactly. Imagine you're trying to predict the weather. You've got all these factors: temperature, wind speed, humidity.
Right.
Melodic invariants are like the heavy hitters in this whole system. They have the biggest influence on what happens.
So kind of like the key players if entanglement was a game or something.
Right, exactly. And it gets even more interesting. This paper, they dig into a specific type of random tensor.
Hit me with it.
It's called a Wishart tensor. Imagine you're trying to study a quantum system, but you only get to observe it partially.
Partially. Like we're only seeing part of the picture.
Exactly. Like you're looking through a foggy window, you get glimpses, but not the full view.
Intriguing. And this is where they bring in the concept of first-order freeness, right? It sounds almost musical.
You're catching on quickly. Essentially, first-order freeness helps us understand these really complex systems by breaking them down into simpler, independent parts.
So kind of like figuring out how each instrument in an orchestra contributes to the overall sound.
A perfect analogy.
Awesome. So we're isolating these tensors, figuring out their individual tunes before we try to understand the whole symphony of entanglement.
You got it. And what's really cool is that this research, they're applying this idea of freeness, which has been used with matrices before, to the world of tensors for the very first time.
I bet that's no easy feat. How do they even begin to apply this to something so multidimensional? But this is where it gets really interesting for our listeners, right? Because this isn't just theoretical anymore. This has some serious implications for how we might actually UE entanglement in the future.
Oh, absolutely. We're talking about things like quantum computing.
Exactly. The potential is mind-blowing.
Imagine building incredibly powerful computers by harnessing this strangeness of entanglement.
Or sending information instantly, securely, anywhere in the universe. That's what we're talking about.
It's true.
Okay, before we get ahead of ourselves and dive into all those exciting possibilities, and believe me, I'm itching to go there, let's take a step back.
Okay.
We need to break down this whole first-order freeness thing a little further, especially how it applies to tensors. All right, so rewind with us for a second, listeners. We're going to look at how this idea plays out in the slightly simpler world of matrices first.
Right. Got to start somewhere.
Exactly. We'll be back in a flash to unpack this whole first-order freeness mystery. All right, so we're back. And honestly, my brain could use a little break after all that talk about tensors and transformations.
I hear you. It's a lot to take in.
It is. But before we go full on tensor, we said we'd rewind a bit.
Right.
Look at how this whole first-order freeness thing works with those matrices we were talking about earlier.
Exactly. Yeah, it's a good place to start.
Okay, back to the basics then. So remind me. What do these matrices have to do with this freeness idea again?
Okay, so picture this. You've got two random matrices, right?
Okay.
Each one, it's got its own little personality, its own set of numbers and properties.
It's like they're each playing their own little tune or something.
Exactly. That's a great way to think about it. Now, if these matrices are independent, meaning they're not influencing each other.
Like two musicians in separate rooms, totally doing their own thing.
Perfect analogy.
Mm-hmm.
Then we can use this idea of freeness to analyze what happens when you kind of combine their tunes.
We're trying to predict what the whole orchestra sounds like, even though each instrument is doing its own thing.
You got it. And first order freeness basically says we can actually predict the properties of that combined system, that orchestral sound, just by understanding the properties of each individual matrix, each individual musician, so to speak. Like if you mix blue and yellow paint, you know you're going to get green, right?
Right.
You don't need to analyze every single pigment molecule.
You just trust the basic rules. Okay, I'm with you so far. But how does this freeness idea work when we scale things up to those, multidimensional tensors? That seems like a whole other level.
Yeah, it definitely gets a little trickier, I'll admit. But that's where these researchers, they introduce something called free cumulants for tensors.
Free cumulants. Okay, gotta be honest, that sounds a little intimidating.
It's not as bad as it sounds, I promise. Think of them like specialized summary statistics.
The summary statistics.
Yeah, they're giving you the most important info about a random tensors distribution.
Okay.
Without getting bogged down in every single detail.
Got it. So it's like a shortcut again, sort of like those trace invariants we were talking about earlier.
You're exactly right.
Yeah.
If trace invariants are like looking at the key performance indicators for a company.
Right.
These free cumulants, it's like reading the executive summary of a really complex report.
Executive summary, I like it. So we're getting the big picture, the need-to-know info.
Exactly.
Okay, so we're getting a handle on these random tensors, but how does that actually help us understand entanglement, especially as it relates to all this first-order freeness stuff.
So here's where it gets really interesting. Just like with matrices, if you have independent random tensors.
Still doing their own thing, those separate musicians?
Right, exactly. They're free cumulants. They have this really cool property. They're additive.
Additive, meaning what? We can just add up the executive summaries of each tensor?
Precisely. And that actually tells us something meaningful about how the whole system behaves.
We're basically combining those individual tunes to understand the whole symphony of entanglement.
I love it. You're getting it. But it gets even cooler. This paper shows that for certain types of random tensors, like those that resemble what we call the pure, complex, Gaussian distribution, kind of a baseline in probability theory, or those Wishart tensors we talked about.
The ones with the foggy window view.
Exactly. They're free cumulants. They actually have a very specific, very telling structure.
So it's not just random noise anymore. We're starting to see some patterns emerge.
Exactly. We're seeing a deeper order within the chaos.
This is blowing my mind a little, I gotta be honest.
And these patterns, they're directly tied to how those tensors actually represent entanglement itself.
Okay, now we're getting somewhere. So by understanding these free cumulants, these little executive summaries, we can actually start to unravel how entanglement works in these complex systems.
Exactly. And that opens up a whole new avenue for not just understanding entanglement, but maybe even controlling it someday.
Okay, now that's what I'm talking about, because this is where it gets really exciting for everyone listening, right? Imagine actually manipulating entanglement.
It's a huge possibility.
Building those ultra-secure communication networks, those super-fast quantum computers. This is a step in that direction.
Absolutely. It's about moving from theory to practical application.
Love it.
And this paper, it really lays some crucial groundwork for that.
Okay, I'm on the edge of my seat.
But there's one more layer to this whole thing that we need to unpack.
Oh, there's more. You're really taking us deep on this deep dive.
We've talked about matrices, tensors, freeness, these free cumulants.
Right.
But there's this word, asymptotic. It keeps popping up.
Asymptotic. Okay, yeah, that one's been floating around. What does that even mean in this context? Okay, asymptotic. So that's a word, right? It sounds a bit intimidating, kind of like something you'd find in a theoretical physics textbook, not gonna lie.
I get it. It's not the most user-friendly word,
Right.
but it's really not that complicated. Think about it like this. What happens when you zoom out on a map, right?
Okay, I'm picturing it.
So when you're all zoomed in, you see all the details, streets, buildings.
Right.
But then you zoom out, right? And those details start to fade away. You get this bigger picture, highways, mountain ranges, the lay of the land.
A big picture, yeah.
That's kind of what we're doing with this asymptotic thinking. We're zooming out, looking at what happens to these systems when they get really, really big.
We're going large scale.
Exactly, to the largest possible scale.
Okay, I'm starting to see the bigger picture here. But we were talking about entanglement, not geography. So what does this zooming out tell us about how these systems actually behave?
So here's the fascinating part. As these systems grow, right, certain properties of entanglement, they become more stable, more pronounced. It's like those first-order effects, those fundamental interactions, they really shine through all the noise.
So the bigger the system, the clearer the signal of entanglement. That's wild. You'd think it would be the opposite, right? Like, things get more chaotic, harder to understand as they get bigger.
It's counterintuitive, for sure. But that's what I love about this kind of research. It's revealing these hidden patterns, this structure within what seems like chaos.
It's like there's an underlying order to the universe.
Right. And this asymptotic perspective, this zooming out, it's crucial if we ever want to build and control these super powerful quantum computers everyone's dreaming about.
Because those would need to be big, right? Big entangled systems.
Exactly. It's like we need to understand the geography of entanglement at a massive scale if we ever want to build the cities of quantum technology, you know.
Wow, I love that analogy. So we're not just talking about some abstract math problem here. This has real implications for how we might actually build these quantum systems in the future.
Oh, absolutely. We're talking about potentially designing very specific types of entangled systems tailored for particular tasks.
Right.
Like, imagine building an ultra-fast quantum computer.
Okay.
Or creating encryption keys that are basically unbreakable.
The possibilities are endless. This is what gets me so fired up about this field.
It's truly groundbreaking stuff.
It is. This deep dive has been quite the journey. We've gone from picturing boxes in multiple dimensions to unlocking the secrets of entanglement. We even took a peek at the future of quantum technology while we were at it.
It's been a wild ride.
It has. But before we wrap up, For our listeners who've been with us on this mind-bending adventure, if they only take away one thing from all of this, what would you say it should be?
That's a great question. I think the most important takeaway here is that randomness, it's not just chaos. Within the randomness, within these quantum systems, there's this hidden order, a structure we can actually understand and potentially even control.
There's hope.
Right. And this research, by looking at these random tensors and their free cumulants, it gives us this whole new way of describing that hidden order, a whole new set of tools for manipulating it.
So, the future of quantum technology. It's out there, waiting to be discovered.
Absolutely. It's a universe of possibilities.
I love it. Well, that's all the time we have for today's deep dive into the world of random tensors and quantum entanglement. Thanks for joining us, everyone. We'll see you next time.
All right, so get ready to
stretch those brain muscles, because today
we are taking a deep dive
into the world of random tensors.
Yeah.
We've got some fascinating research to unpack.
Trust me, this is way more interesting than it sounds.
It really is. We're going beyond the usual tensors are just multi-dimensional spreadsheets analogy. This research dives into how these mathematical objects behave in a random setting, and the implications are huge for fields like
quantum physics and machine learning.
Okay, so let's start with the basics. We're looking at excerpts from Free Cumulants and Freeness for Unitarily Invariant Random Tensors. Now, I get that tensors are all about relationships between things, but what makes them random in this context?
Imagine you're building a network, but instead of fixed connections, you're using some kind of probability to determine how things link up. That's what we're dealing with here. Tensors with an element of randomness baked in.
So instead of saying point A is definitely connected to point B, we're saying there's a chance they're connected.
Precisely. And what makes this research so compelling is that it explores what happens to these random tensors as the system grows infinitely large, what they call asymptotically. Think of it like trying to predict the weather. A small localized system might be easier to predict.
But as you factor in more variables, things get exponentially more complex.
And that's where these researchers come in trying to make sense of the chaos.
Exactly. They're looking for patterns and hidden structures within this randomness using these things called cumulants. It's like finding constellations in a seemingly random scattering of stars.
Okay, I'm intrigued, but I've got to be honest. Cumulants sounds like something out of a science fiction movie. Can we break that down a bit?
Sure. Think of cumulants as a way to measure the interconnectedness of random variables. They go beyond simple averages and reveal those subtle dependencies that wouldn't be obvious otherwise.
So it's like they're giving us X-ray vision into the hidden workings of these random tensors.
I like that analogy. And what they're finding is that these cumulants are key to understanding a crucial concept called freeness.
All right, so we've got cumulants, we've got freeness. I'm sensing some serious brain bending ahead. Give me the lowdown on freeness. Why does it matter?
In simple terms, freeness tells us how independent these random tensors are from each other. Imagine trying to predict the stock market where everything is intertwined. Now imagine a market where stocks are free. Their prices move independently. That's the kind of analytical power freeness gives us.
So if we know how free these random tensors are, we can make more accurate predictions about how they'll behave in the long run.
Exactly. It's like having a crystal ball, but instead of vague predictions, it's giving us precise mathematical insights.
Okay, I'm starting to see the light. But how do we actually visualize these random tensors? They're operating in multiple dimensions, right?
You're right. Traditional graphs and charts won't cut it here. That's where those wild tensor diagrams you see in the paper come in.
Think of them as a visual language specifically designed to represent these complex relationships.
So like a roadmap for navigating the tensorverse. I'm picturing something out of Interstellar right now.
Exactly. And those diagrams aren't just pretty, they reveal underlying structures. Some, called melonic, are like finding repeating patterns in a mosaic. It hints at a deeper order within the randomness.
Melonic, like a watermelon shape.
Not quite as delicious, though. I admire the attempt to find a tasty analogy. They're named after a specific mathematical pattern. These melonic structures are more predictable than other types of tensors, and understanding them is key to unraveling the mysteries of this research.
Okay, so we've got these melonic structures that are like the predictable patterns within the randomness of these tensors. Where do we go from here?
That's where things get really interesting. The researchers discovered that these structural differences, melonic versus non-melonic, actually impact how free these random tensors are.
Hold on, you're blowing my mind a little here. You're saying the shape of these tensor diagrams can tell us how independent they are.
Exactly. It's like discovering that the arrangement of atoms in a material determines its conductivity or melting point. Structure dictates behavior. And this is where those cumulants we talked about earlier come back into play. They're the mathematical tools that allow us to quantify these differences in freeness.
All right, so the cumulants are like our measuring sticks, helping us see how much freeness is present in these random tensors. What kind of results are we seeing? Are all random tensors created equally free?
That's the fascinating part. The researchers dove into different flavors of random tensors, and what they found is that freeness isn't a one-size-fits-all concept. Some types of random tensors are inherently more free than others.
Okay, now you have to give me some examples. What kind of flavors are we talking about here?
Let's start with the Gaussian tensors. These are kind of the vanilla flavor, the simplest type, where the values follow a normal distribution. The researchers found that these Gaussian tensors exhibit something called asymptotic freeness.
Asymptotic freeness. So as these Gaussian tensors grow larger, they become more and more independent, like they're breaking free from any constraints.
Exactly. It's a remarkable finding. But when the researchers looked at other types of random tensors, like the Wishart tensors, which are built from these Gaussian ones, they found something different.
Let me guess, the Wishart tensors didn't quite embrace the free life as readily as their Gaussian counterparts?
Precisely. They discovered that Wishart tensors, even as they grow larger, still have some level of dependence baked in. They're not as free as the Gaussian tensors. It's like comparing a group of solo artists to a band. The individual members might have their own style, but they're still influenced by the group dynamic.
That's a great analogy. So different flavors of random tensors have different levels of freeness, and we can use those cumulants to measure those differences. But why should we care? You've hinted at some pretty big implications.
Right, and this is where things get really exciting. Understanding freeness in the context of random tensors has the potential to revolutionize how we approach complex systems in various fields. We're talking about everything from quantum mechanics to artificial intelligence, even finance.
Wow, okay, so we're not just talking about abstract mathematical concepts here. These insights could have real-world applications.
Absolutely. Take quantum computing, for example. One of the biggest challenges in that field is modeling and simulating quantum systems, which are notoriously complex and counterintuitive.
Because quantum mechanics is basically magic, right? At least that's what it feels like sometimes.
Pretty much. But random tensors, with their ability to capture those complex dependencies and long-range correlations, could provide a more natural and powerful framework for understanding and simulating these systems. Imagine being able to design more efficient quantum algorithms or even build more powerful quantum computers, all thanks to a deeper understanding of freeness in random tensors.
Okay, that's officially mind-blowing. What about artificial intelligence? How could this research impact that field?
Well, at its core, machine learning is about finding patterns in data. But as data sets become increasingly complex, traditional algorithms start to struggle. They're not equipped to handle millions, even billions of variables interacting in intricate ways.
It's like trying to make sense of a billion-piece jigsaw puzzle without a picture to guide you.
Exactly. But imagine if we could develop new machine learning algorithms based on the principles of random tensors, specifically their ability to capture and analyze those complex relationships in high-dimensional spaces. We could potentially unlock entirely new levels of pattern recognition and predictive power.
So we're talking about AI that can make sense of the chaos, that can find those hidden signals in the noise. That's incredible. And you mentioned finance as well. How does this all tie into that world?
Well, think about the stock market. It's a perfect example of a complex system with countless variables influencing prices. Traditionally, financial models have relied on simplifying assumptions to make predictions.
But we all know how well those predictions tend to work out, right?
Right. But imagine if we could apply the insights from random tensor theory to build more robust and accurate financial models. Models that can account for those subtle dependencies and long-range correlations that traditional approaches miss. It could revolutionize how we manage risk and make investment decisions.
I'm starting to see a pattern here. It seems like random tensors have the potential to be a game changer across so many different fields. This is much bigger than I initially realized.
It really is. We're just scratching the surface of what this research could unlock. And the researchers themselves acknowledge that there's still so much more to explore.
You've definitely given us a lot to think about. But for those of us who aren't mathematicians, where do we go from here? How can we delve deeper into this world of random tensors?
Well, I always encourage people to embrace their curiosity. There's some fantastic resources available online, even for those who don't have a background in advanced mathematics. Start with the basics of tensors and work your way up.
It's like learning a new language, right? You start with the basic vocabulary and grammar, and before you know it, you're having full-blown conversations.
Exactly. And don't be afraid to explore those tensor diagrams we talked about. They might seem intimidating at first, but they're actually a very intuitive way to visualize these complex relationships. There's some great tutorials available that break them down step by step.
So we've got the resources we're building up, our tensor vocabulary. What else can we do to really solidify our understanding?
One thing the researchers emphasize is the importance of exploring higher-order interactions within these random tensors. It's like we've mapped out the continents, but now we need to zoom in and explore the intricate details of each region.
So we're going from a bird's eye view to a street-level perspective, trying to understand the nuances of how these tensors interact on a deeper level.
Precisely. And the researchers believe that understanding these higher-order interactions could hold the key to even more profound discoveries, potentially leading to entirely new mathematical frameworks and applications that we can't even imagine yet.
That's both exciting and a little bit terrifying, isn't it? It's like we're standing at the edge of the unknown.
Absolutely.
Yeah.
And the other big question that the researchers are grappling with is the broader implications of asymptotic freeness. We've talked about how it applies to certain types of random tensors, but there's still so much we don't know about how it plays out in different contexts.
So we've seen how some of those ships sail solo, but now we need to figure out what happens when they encounter a whole fleet of other ships. How does their freedom change within a more complex and interconnected system?
Exactly. And how does freeness itself evolve as we introduce more variables, more dimensions, more complexity? These are questions that will keep researchers busy for years to come.
And hopefully lead to even more mind-blowing discoveries that will change how we understand the universe. It seems like the study of random tensors is really pushing us to rethink our assumptions about the nature of randomness itself.
I think you're right. We often think of randomness as the opposite of order, as something unpredictable and chaotic. But this research suggests that there might be a deeper order within that chaos, a hidden structure that we're only beginning to glimpse.
That's a pretty profound thought to end on. It seems like every time we answer one question about random tensors, we uncover a dozen more.
That's the beauty of scientific exploration, isn't it? The more we learn, the more we realize how much more there is to know. And in this case, that journey of discovery has the potential to reshape our understanding of everything from the smallest particles to the largest structures in the universe.
Well said. I think it's safe to say that our brains are officially full for today. To everyone listening, thank you for joining us on this incredible deep dive into the world of random tensors. Keep those minds curious, and we'll catch you on the next episode as we explore another fascinating corner of the knowledge universe.
Ever feel like some areas of science are just speaking a different language?
Yeah.
Like you're at a party and everyone's talking about stuff you just don't get.
Yeah, I know that feeling.
Well, that's what we're tackling head on today. We're diving deep into a paper called Free Cumulants and Freeness for Unitarily Invariant Random Tensors.
Catchy title.
Right. Don't worry, we'll be sure to translate the jargon as we go.
That's probably for the best. But it's a fascinating paper, really. It kind of reveals these hidden connections between parts of math that you wouldn't expect. And it all starts with these things called tensors.
Okay, so right off the bat, what is a tensor? Is that like some futuristic tech in Star Trek? What are we talking about here?
Less sci-fi, more like advanced organization. I guess the easiest way to think about it is like, a list of numbers. That's a vector, right?
Okay, I'm with you.
Then a grid of numbers, that'd be a matrix. And a tensor, that's like a whole cube of numbers.
Okay.
But it can have even more dimensions, like way more, just to really blow your mind.
So it's basically a way to organize a ton of data. But why is that so important? What's the big deal with all these numbers?
Because so much in the real world, it's multidimensional, right? Like take machine learning. Those algorithms that can recognize faces in photos, tensors, that's how they're representing all that image data.
Oh, interesting. So instead of seeing a picture like we do, the algorithm is seeing a tensor.
Exactly. It's all numbers arranged in this super complex tensor shape. And it's not just machine learning either. Tensors. They're how we understand space-time and Einstein's theory of relativity, too.
Wow, okay.
Kind of big deal.
Big deal is an understatement. Okay, I'm starting to see why these things are important, but now I've got to add in this random element. What in the world is a random tensor?
Okay, so picture this. You're filling up that multidimensional cube with numbers, but instead of picking them out, you're using a random number generator.
Okay, so just chaos in a cube. Got it.
Well, not complete chaos. There are rules. These random numbers, they follow certain probability distributions, like a bell curve you might have seen.
Ah, okay, so it's like flipping a coin, right? Like it could be heads or tails, totally random in the moment, but flip it enough times, you expect a pretty even split.
Exactly. And the cool thing is, by studying the patterns in these random tensors, we can actually figure out hidden structures and relationships.
So it's like those magic eye pictures where you have to, like, relax your eyes to see the image in all the random dots.
Perfect analogy. Now, this paper we're looking at, it zeroes in on a special kind of random tensor. They have this property, it's called local unitary invariance, LU invariance for short.
LU invariance.
Yeah.
Does that give you, like, superpowers in the math world?
Well, it's kind of a mathematical superpower for these tensors, yeah. Basically, they don't change even if you rotate the coordinate system. Imagine looking in a mirror. Your reflection's flipped, but you're still you, right?
Right. Still me.
Yep.
It's backwards.
Exactly. Same idea. These tensors are like chameleons blending into different coordinate systems, but their core properties, those stay the same.
Okay, so they're like the James Bond of the math world. Super adaptable.
Yeah, they're pretty cool. And this whole LU invariance thing, it turns out it's really useful for describing some pretty crazy physics, like quantum entanglement.
Okay, entanglement. Now we're getting into some seriously complex stuff. But before we get ahead of ourselves, how do mathematicians even begin to study these random tensors? It seems like you're trying to decipher a code written in randomness.
Well, that's where these things called moments and cumulants come in.
Moments and cumulants. You're just messing with me now, right?
I promise. It's not as complicated as it sounds. Think of moments like they give you the basic stats of a data set, like the average, how spread out the numbers are, that kind of thing.
Okay, so moments are like a quick snapshot of the data's personality.
Exactly. Now, cumulants, those are the real detectives. They go beyond the basic stuff and reveal the more hidden, subtle relationships within the data.
Yeah, they're like, those detectives in movies, the ones who notice the fingerprints at the crime scene.
Okay, I'm picturing it. They don't match anyone, and that's the clue. That something way more complicated is going on.
So they're the ones who crack the case wide open. So in the case of these random tensors, what clues are the cumulants revealing? What's going on?
Well, that's where this paper gets really interesting. It introduces this new way to calculate, they're called free cumulants, specifically for these LU invariant tensors.
Free cumulants. All right, now I'm definitely lost in the weeds here. Why is this new calculation such a big deal?
It's a big deal because it opens up all these connections to other areas of math and physics. Like, remember how we talked about those LU invariant tensors being so good at describing quantum entanglement?
Right, all that spooky action at a distance stuff. You promised we'd come back to that.
I always deliver. And it turns out, understanding these free cumulants gives us a whole new way to look at and understand entangled quantum states.
Okay, hold on. Before we fall down the quantum rabbit hole, let's take a step back. What even is entanglement, really?
Okay, so imagine this. You and I, we both have a coin, right? We flip them at the exact same time. In the normal world, what happens? My coin flip doesn't affect yours. They're totally separate.
Right, two totally random events.
Okay, but in the quantum world, you can have two particles, like our coins, but they're linked. So if you measure one and it's heads, you instantly know the other one is tails, no matter how far apart they are.
Whoa, wait. So it's like those coins are secretly talking to each other faster than the speed of light?
It really is a mystery, and it's that impossible connection that makes entanglement so fascinating and so potentially powerful for things like quantum computers, for example.
Okay, I'm starting to see why everyone's so excited about entanglement. But where do these LU invariant tensors fit into all of this?
Well, think about it. Just like those coins have that hidden connection, these tensors, they have this unique symmetry, right? Remember, they don't change even if you rotate them every which way.
Right, yeah.
And that symmetry, it mirrors the way entanglement itself behaves. Like, it doesn't matter how you're looking at those entangled particles, the entanglement stays the same.
So the tensors are basically a mathematical mirror of this whole entanglement thing.
Exactly. They give us a way to actually describe and study this crazy phenomenon.
That's incredible. But you mentioned something even weirder earlier, a connection between random tensors and topology. Now we're going from the quantum realm to straight up abstract math.
And that's what makes this paper so cool. It connects those two worlds. So to get there, let's imagine something a little more familiar, a donut.
A donut? Are we taking a snack break? I could use a donut right about now.
Not quite. Think about the shape of a donut. It's got that one hole in the middle, right? Mathematicians, they call that genus 1. A sphere, like a basketball, it doesn't have any holes, so it's genus 0.
Okay, got it. Donuts, spheres, holes. I'm with you. But how do we get from the number of holes in a donut to these mind-bending random tensors?
That is the million-dollar question. And this is where the paper gets really exciting. It shows us this link between the genus of certain mathematical objects and the behavior of these random tensors.
Wait, hold on. So you're telling me there's a connection between the shape of a donut and the statistical properties of random numbers arranged in multiple dimensions?
I know, it's wild, right?
It's mind-blowing.
It's like finding this secret tunnel between two rooms that you never knew were connected. And it points to a much deeper, more fundamental relationship between parts of math that we always thought were totally separate.
I'm following you. I really am.
Yeah.
But why is this connection such a big deal? Why should we care about this hidden tunnel between donuts and random tensors?
Now you're asking the big questions. It's a great question because it forces us to look at the bigger picture. This might seem abstract, but this connection, it could totally change how we understand the universe. Especially when it comes to quantum gravity.
Quantum gravity. All right, now we're going full-on theoretical physics here.
That's where all the cool stuff is, right?
Okay, alrighty. Take me down the quantum gravity rabbit hole. How does all this tensor stuff connect?
Okay, so quantum gravity, this is it, right? It's like the holy grail of physics.
Big question.
The big one. We're trying to find a theory that finally puts together Einstein's theory of general relativity, which explains gravity on those huge scales like planets and galaxies.
Like big stuff.
For quantum mechanics, which explains the super tiny world of atoms and particles.
So it's like finding one set of rules for how everything works.
Yeah.
From the smallest thing to the biggest.
Yeah, that's it. But it's tough, man. One of the biggest problems is that these two theories, they see space and time totally differently.
Okay, yeah, that sounds like a bit of a problem.
Yeah.
So where does topology come in? Is that the magic bridge?
Well, some physicists, they think topology might be the key. Remember those donuts and spheres we were talking about?
Yeah, still makes me hungry.
Right. But topology, it's all about the core properties of shapes, the things that don't change, even if you stretch it or squish it.
So like a coffee mug and a donut are basically the same, topologically speaking.
Exactly, one hole each. And the idea is some physicists think space-time itself. It might have these hidden topological features, and those become important at the quantum level.
Wait, so are you saying that the fabric of space and time could be like some kind of giant cosmic pretzel with like loops and twists we don't even see?
Hey, stranger things have been theorized. And this is where our random tensors come back into play, that weird connection we found between how they behave and these topological properties. It could be a whole new way to think about the quantum nature of space-time.
So all this time, these random tensors, these abstract mathematical objects, they might hold the key to the biggest mystery of reality.
It's a possibility. And even if it doesn't lead us straight to quantum gravity, this research is already pushing the limits of what we know about math and physics, both.
This paper is like a Pandora's box of insane ideas. It really blows my mind how these different areas of science, they're all connected. We started with random tensors, and somehow we ended up talking about the fate of the universe.
That's what I love about this field, honestly. You never know where it's going to lead. And with random tensors, we're just scratching the surface. Who knows what other secrets are out there just waiting to be discovered?
I feel like I need to go back and listen to this whole thing again just to process it all.
That's the best way to do it. Hopefully this deep dive sparked some questions, maybe even inspired some future physicists and mathematicians out there.
It definitely sparked something in me. This was a wild ride. Thanks for joining us on this incredible journey, and until next time, keep those brains buzzing. Hey there. You ready to dive into some seriously cool math today?
Always up for a challenge. What are we tackling?
We're taking on free cumulants and freeness for unitarily invariant random tensors.
It's a mouthful, I know.
Sounds intense.
It is, but it's got some seriously cool applications. We're talking quantum information theory, machine learning, the works.
Okay, you've piqued my interest. So what's the deal with these unitarily invariant random tensors?
Well, this paper, it's basically trying to figure out how these things called random tensors will behave, especially if they have this thing called local unitary invariance.
Ah, local unitary invariance, or LU invariance for those in the know.
Exactly.
Basically, it means that even if we rotate the system, those key properties, they don't budge. They're rock solid. Think of it like a mathematical spinning top. No matter how much you twist it, it keeps its balance. Okay, I think I get it. But before we go any further,
Yeah.
can we rewind a bit? What even is a tensor? I'm picturing like some futuristic sensory device, honestly.
Haha, I see where you're coming from, but it's not quite that exciting.
Wow.
Think of a tensor as a way to organize a bunch of numbers. Imagine a spreadsheet that's a two-dimensional tensor. Now picture a whole stack of those spreadsheets, one on top of the other that's getting closer to what we mean by a higher dimensional tensor.
Okay, so like a multi-dimensional grid of data. But how do we even begin to understand something that complex?
Well, that's where things get really interesting.
This paper keeps mentioning trace invariants. What are those all about?
Trace invariants, they're like fingerprints for each tensor. They cut through the noise and show us the essential properties of a tensor no matter how we manipulate it.
So they're like the key to unlocking the secrets of these tensors.
Exactly. And this is especially important when we're dealing with quantum information and that strange world of entanglement.
Entanglement now, that's a whole other deep dive waiting to happen, right?
Definitely.
But for now, can you remind us why this LU invariance is so important, especially in the quantum realm?
Absolutely. You see, in quantum information, we're often doing things that are like rotations, but in a very abstract space.
Okay.
And LU invariance makes sure that the fundamental relationships in the system, like the entanglement between particles, stay rock solid even after we perform these rotations.
So it's like the quantum equivalent of an unbreakable bond no matter how much we mess with it.
Exactly. It's pretty amazing. And this is where our usual ways of analyzing random systems start to struggle. We usually use tools designed for matrices, which are like simpler versions of tensors.
Okay.
But with tensors, especially those with LU invariance, those tools, they just don't cut it. We need a serious upgrade.
Time for some new mathematical toys then. All right, so before we went off on that little tangent, we were about to dive into Gaussian scaling.
Ah, yes. Gaussian scaling.
It sounds a bit intimidating, not gonna lie.
It's not as scary as it sounds. Think back to how we were talking about tensors being like multi-dimensional grids of numbers.
Right, like a whole stack of spreadsheets.
Exactly. Gaussian scaling helps us understand how those numbers are spread out, how they're distributed.
Okay.
Imagine looking at the heights of everyone in a huge crowd. Most people are going to be around average height, right? Fewer people at the extremes.
Yeah, the classic bell curve.
Exactly. And Gaussian scaling tells us that the values in these random tensors, they tend to act in a similar way.
So it's like a blueprint for randomness.
Yeah.
Even if we don't know the exact number, we have an idea of what to expect.
That's a great way to put it. And this is especially helpful when we're trying to wrap our heads around a specific type of random tensor.
Let me guess. The pure complex Gaussian tensor.
You got it. Think of it as like the default setting for randomness in the world of tensors.
Okay, so the pure complex Gaussian tensor, it's like our starting point. What tools do we have to analyze it? The paper keeps mentioning melonic invariants. What are those all about?
Melonic invariants. Oh, they're fascinating. Imagine them as like special lenses that help us see the patterns hidden within the randomness.
Okay, I like where this is going.
Imagine you're trying to predict the weather. It seems super random and chaotic, right?
Yeah.
But meteorologists use underlying patterns and relationships to make their forecasts.
Right.
Melonic invariants are kind of like those patterns, but for tensors, they show us the structure within these seemingly random systems.
So we're not just looking at a jumble of numbers anymore. We're starting to see the connections. What I find really cool is that the paper actually shows what these melonic invariants look like. They're beautiful.
They really are. And it gets even more interesting. Not all invariants are created equal.
What do you mean?
Well, there's this idea of orders of dominance.
Mm-hmm.
Basically, some invariants have a way bigger impact on how the tensor behaves overall, especially as it gets larger and larger.
So it's like in a symphony orchestra, you've got all these different instruments, but some, like the booming timpani drums, they carry the main melody, right?
Exactly. And being able to pick out these dominant invariants, it's incredibly useful. It lets us focus on what's really important and ignore the noise.
Finding the signal in the noise. But once we've got a handle on these pure Gaussian tensors, can we actually use this knowledge for the messier, more realistic systems?
You're on the right track. The paper then goes on to explore perturbed Gaussian tensors.
Perturbed.
It's just a fancy way of saying the randomness is tweaked a little bit, makes them a better reflection of the real world.
Okay, makes sense.
But here's where things get really wild. As we go up in dimensions, like adding more and more spreadsheets to our stack, things get really strange.
Wait, are you saying randomness itself gets weird in higher dimensions?
In a way, yes. The way we usually think about randomness. It works fine in lower dimensions. but in those higher dimensions, our intuition starts to break down. And it's especially obvious in dimension 6.
Dimension 6, huh? It's like we've stumbled upon a secret level where the rules are totally different. But before we get too lost in the mysteries of higher dimensions, we should probably talk about another important character, the Wishart tensor. I'm getting the sense that it's like a pure tensor that's gone through some stuff. Maybe you had some information redacted.
That's a fantastic analogy. You see, a Wishart tensor comes about when you take a pure tensor and trace out some of the information, which leaves us with an incomplete picture.
So, like trying to solve a puzzle with missing pieces. Why is this Wishart tensor so important?
Well, if you've been keeping up with those sources on quantum information theory, you might recognize this whole tracing out business. It's a lot like dealing with mixed quantum states, where we only have limited info about the system.
Ah, so the Wishart tensor helps us navigate the quantum world when we don't have all the answers. What's impressive is that this paper doesn't just stop at introducing the Wishart tensor. It goes a step further.
You're right. It develops specific tools to analyze them. Just like we have tools for those pure Gaussian tensors, we've now got ways to figure out these more complex, mixed tensors as well.
It's like we're leveling up our mathematical toolkit.
Exactly. And one of the most powerful tools in this new kit is something called free cumulants.
Free cumulants. That sounds a bit intimidating, even for this deep dive.
They're amazing. They let us analyze both pure and mixed random tensors. We can even figure out if two tensors are truly independent or if they're somehow connected.
So, like relationship detectives for tensors. I bet this is ringing a bell for our listeners who are into probability and statistics.
You know it. Free cumulants are a big part of free probability, a branch of probability theory made just for dealing with things like matrices and tensors.
Okay, so we've got all these powerful tools for analyzing random tensors, pure and mixed, but wow, this has been a lot. Can you remind us why this even matters? What's the big takeaway here? Okay, so we've got all these powerful tools for analyzing random tensors, pure and mixed, but wow, this has been a lot. Can you remind us why this even matters? What's the big takeaway here?
It's like we've been handed this amazing new toolkit, right? We can use it to understand complexity in a whole new way. And these random tensors, they're everywhere. Quantum mechanics, the algorithms running in our phones, everywhere.
So this isn't just some abstract math problem.
Not at all. This is real-world stuff.
Like what? Give me an example.
Okay, so in quantum information, we're using these tools to build better quantum computers, more powerful ones.
Wow.
And we can simulate these crazy complex quantum systems all thanks to these tools. And in machine learning, forget about it. We're talking faster algorithms, better predictions, all because we can analyze huge data sets in ways we couldn't before.
So it's like pushing the boundaries of what's possible, but in all these different fields at the same time.
Exactly. And the thing is, we're just getting started. There's so much more out there to find.
Especially in those higher dimensions you were talking about earlier, right?
Yeah.
Where everything we thought we knew about randomness goes haywire.
Exactly. Dimension 6 and beyond. That's where the really cool stuff is happening. It's like a whole new universe of math and physics just waiting to be explored.
I don't know, those uncharted territories.
Yeah.
It's a little intimidating.
It's a little like staring into the abyss, isn't it?
A little.
But think about it. Every big discovery, it started with someone being a little curious, a little bit brave, willing to face the unknown.
You're right. It's about pushing past what we think we know and being open to, well, everything.
Exactly.
This whole deep dive has been amazing. Thank you so much for walking us through all of it. Random tensors, who knew?
It's been my pleasure. And that's the beauty of this field, right? There's always something new to discover, no matter how deep you go.
You've definitely sparked my curiosity. To our listeners, if you're feeling inspired, don't stop here. Go check out the paper we talked about, dive into quantum information, or just spend some time thinking about those higher dimensions, the possibilities. They really are endless.
You said it.
And on that note, we'll wrap up this deep dive. Until next time, keep those questions coming, keep exploring, and most importantly, never stop learning.
All right, ready to dive in. Today, we're looking at free cumulants and freeness for unitarily invariant random tensors.
Yeah, it's a mouthful, but it's a really interesting paper, actually.
Well, right.
It's not just about what these random tensors are. It's really about how we can understand them,
Yeah.
analyze them. It's like we're figuring out the tools to map out some completely uncharted territory.
Ooh, I like that. A map for uncharted territory.
Yeah.
But for those of us who maybe haven't encountered tensors before, can we just take a step back?
Sure.
What are they? Why is randomness important here?
Okay, so think about like a single data point, just a number, right? Then you've got a spreadsheet, you've got rows and columns, that's a matrix.
Okay.
A tensor takes that idea further. It's like a multi-dimensional cube of data.
Right.
And we use them to represent these really complex relationships. Like you see them in physics, machine learning, quantum information theory.
Of course, yeah.
And the random part is, well, just like we use random numbers for simulations.
Yeah.
Random tensors help us model all these systems where the individual parts, they behave kind of unpredictably.
Right.
But when you zoom out, you start to see these patterns.
It's that order and chaos thing, which I always find fascinating, but we're talking about multiple dimensions here.
Exactly.
And that's where this paper's focus on unitarily invariant random tensors comes in, right?
Yeah, yeah.
I'll be honest, it's always a bit of a head scratcher for me.
It's a mouthful, I know. Think of it this way. Imagine you're looking at a sculpture.
Okay.
You can walk around it. You can look at it from different angles.
Right.
But its fundamental properties, its shape, its volume, they stay the same.
Right, right.
So unitary invariance, it's similar. Certain properties of these tensors stay constant even when we apply these really complex transformations. It's like rotating that sculpture.
So it's like rotationally invariant, but in a much more abstract space.
Exactly, yeah.
And it's not just a mathematical curiosity, right? This invariance has real-world implications, especially when we start talking about quantum mechanics.
Yeah, you hit the nail on the head. Unitary invariance is super important in quantum information theory.
Okay.
Because it's directly related to how these entangled quantum states behave.
Right, those spooky particles that always seem to know what the other one's doing. So we have these multidimensional objects, tensors, they can be random, and the ones we're interested in have this very specific property of unitary invariance.
Yeah.
Which is especially important in that quantum realm.
Yes.
Okay, but this is where the real meat of the paper comes in, right? It's not just about defining these things, it's about how we actually analyze them.
Exactly. And that's where it gets really interesting. This paper, it dives into some really cool mathematical tools to characterize these random tensors, to figure out their secrets, the patterns hidden within the randomness.
And those are the tools that we're going to be unpacking in part 2.
Right.
Because it's not enough to just look at a bunch of numbers in a multidimensional cube and go, yep, that's a tensor.
Right.
We need a way to actually make sense of it all.
We need the right map to navigate this uncharted territory.
Love it. Okay, we're going to take a quick break, and we'll be right back to unpack those tools. Okay, so we've set the stage.
Yeah.
We've got these unitarily invariant random tensors, these kind of multi-dimensional puzzles, right? With like clues to the universe hidden inside.
Exactly.
But we need the right tools to unlock those secrets.
Yeah.
So where do we even begin with analyzing something this complex?
Well, that's where the real beauty of this paper comes in.
Okay.
It introduces these pretty powerful mathematical concepts,
Yes.
moments, and free cumulants.
Okay.
Now, stick with me here,
Yeah.
because they're not as scary as they sound.
Yeah.
Think of them like specialized lenses,
Okay.
each one revealing different aspects of a tensor's hidden structure.
Here. So how do these lenses, these moments and free cumulants, how do they actually help us make sense of what's going on inside a random tensor?
Okay, imagine you're trying to like understand a city's layout.
Okay.
But instead of a map, you just have like all these data points scattered across this 3D model, right?
Yeah.
Moments, they give you a sense of the overall distribution.
Okay.
Like where are the clusters? How spread out are things?
Right.
Free cumulants, though, they zoom in on the connections between those clusters,
Okay.
revealing how different parts of the city actually relate to each other.
So moments are like getting a sense of the city's density, and then free cumulants are like showing us the underlying infrastructure that works.
Yeah, it's like seeing the city's skeleton,
Yeah.
the framework that gives it shape.
And what makes this paper even more interesting is how it explores these different types of random tensors.
Right.
Specifically, mixed and pure ones.
Yeah.
Now, help me understand the difference there.
So think about the difference between like a symphony orchestra.
Okay.
That's your mixed tensor, right?
A lot going on.
A combination of all these different elements versus a lone violinist playing a single pure note.
Right.
That's your pure tensor.
So a pure tensor is like this single unified entity.
Exactly.
Whereas a mixed tensor is more like a combination of different components,
Yeah.
each with their own kind of unique properties,
Precisely.
but both essential in their own way.
Absolutely, yeah, just like we need both soloists and orchestras, right?
Exactly. But where do we actually encounter these different types of tensors in research?
Well, let's take quantum entanglement, for example.
Okay.
Remember those weirdly connected particles we were talking about?
Yeah.
It turns out that mixed tensors, specifically a type called Wishart tensors, they're incredibly useful for modeling and understanding those entangled states.
Oh, okay.
They help us capture those complex correlations even when the particles are separated by, like, huge distances.
So we've got our different types of tensors. We're using these mathematical lenses moments and free cumulants to analyze them.
Yeah.
But I feel like there's another layer here.
Yeah, right.
Another tool in our kit for understanding these complex beasts.
Yeah, there's one more crucial piece.
Okay.
It's a technique called asymptotic analysis.
Okay.
And it's like, imagine you're looking at a tapestry, right?
Yeah.
Up close, all you see are the individual threads. But as you step back, this larger pattern emerges.
Yeah.
Asymptotic analysis. It's about understanding how these tensors behave as they grow infinitely large.
Okay.
So we can see those big picture patterns hidden in all the complexity.
So instead of getting lost in the weeds, we're taking a step back,
Exactly.
seeing the forest for the trees.
Yeah.
And this approach, this asymptotic analysis, it unlocks something pretty remarkable about these random tensors, doesn't it?
It does. This is where the paper's findings get really groundbreaking.
Okay.
It introduces these things called melonic invariants.
Melonic invariance.
Yeah, there's specific patterns within these tensors
All right.
that become increasingly important as the tensors get larger.
So like recurring motifs in this tapestry we were talking about.
Exactly.
Okay, I'm picturing these like elegant structures within the chaos. Yeah.
Like mathematical constellations.
Right.
But why are these melonic invariants so important? Especially in the context of Gaussian random tensors, which is what this paper focuses on.
Because Gaussian random tensors, where the data points are drawn from that, like classic bell curve,
Right.
they're like the bedrock of so many fields.
Okay.
And what this paper shows is that these melonic invariants, they're especially prominent in Gaussian random tensors.
So it's like they form the backbone of their structure.
Exactly.
So we've gone deep into this world of random tensors, and we've got all these tools, these moments, these free cumulants,
Right.
asymptotic analysis, melonic invariance.
That's a lot.
It is.
Yeah.
But let's zoom out for a second.
Sure.
For someone who might not be a mathematician but is listening, like,
Yeah.
why does all this matter? What's the big deal here? Well, because understanding these random tensors, it's like getting a new lens to look at the universe, right?
Right.
Their applications, they're everywhere.
Yeah.
Data science, machine learning, quantum mechanics, you name it.
Give me some concrete examples then, because I'm all about those.
All right, so let's take machine learning, right?
Sure.
It's already changing everything.
Yeah, it really is.
Facial recognition, personalized recommendations.
Right.
All those algorithms, they rely on finding patterns in these massive data sets.
Right.
Data sets that are often structured as, you guessed it, tensors.
So instead of those neat rows on a spreadsheet, we're
Yeah.
talking about data that has all these dimensions,
Exactly.
capturing all those complex relationships between different features.
Exactly. Yeah, it's like instead of analyzing one photo,
Right.
you're analyzing thousands at the same time, each one with all these different tags and attributes.
Okay, so much more complex.
Way more complex.
And this is where those melonic invariants come into play.
This is it. By understanding those recurring patterns, especially the Gaussian ones,
Okay.
we can design machine learning algorithms that are way more efficient.
Okay.
They can cut through all that data, find those hidden relationships.
So we're like giving these algorithms a boost.
Exactly. A shortcut to finding meaning in all that data overload.
I like it.
And it's not just speed.
Okay.
It's about making them smarter.
Right.
By using those unique properties of random tensors, how they behave as they grow. Remember asymptotic analysis.
Yeah.
We can build AI that's way more adaptable,
Right.
able to handle the messiness of real-world data.
That's amazing. But we talked about machine learning.
Yeah.
What about those other areas like quantum mechanics? That's where things get really wild.
Oh, absolutely.
Right.
So remember how we talked about unitary invariance being super important for understanding entanglement?
Yeah, that spooky action.
Exactly. Well, the tools from this paper, especially for those mixed tensors, like Wishart tensors,
Okay.
they give physicists this whole new way to model and simulate these entangled systems.
So we're talking about potentially revolutionizing our understanding of entanglement itself.
Exactly. And that has huge implications.
Right, like Quantum computers, unbreakable encryption, all that.
All of that, it all ties in. And I think the most mind-blowing thing about this paper
Yeah.
is that it highlights this really elegant connection between randomness and order. It shows us that even in these random tensors, there are these predictable, beautiful patterns just waiting to be discovered.
It's like we're finding the hidden code of the universe.
Right.
There's order in the chaos.
Exactly.
Was there a particular aha moment in the paper for you that really drove that point home?
There was. They talk about asymptotic freeness.
Okay.
And that's really profound because it shows that as these random matrices, which are a type of tensor,
Okay.
as they get bigger and bigger, they start behaving in these really predictable ways.
So it's like even randomness has its own rules.
Yeah, like given enough space, randomness reveals its own order.
Wow.
It's pretty amazing.
That is amazing. So it's not just a mathematical curiosity.
Well, no, at all.
It changes how we think about randomness itself.
It really does.
Yeah.
It suggests that what we think of as random might actually be governed by these deeper mathematical principles.
And these tools, the moments, the free cumulants, all of that, they're giving us a glimpse into those deeper principles.
Exactly.
This has been incredible. We started with these abstract mathematical objects.
I know, right?
And now we're talking about revolutionizing AI, quantum physics.
And we're just getting started.
Right.
This paper, it's like the foundation,
Yeah.
the tools we need to keep exploring.
There's so much more to discover.
Absolutely. This is just the beginning.
And to our listeners, we encourage you, keep that curiosity going, keep diving deeper into this world of random tensors. Who knows what other secrets are out there? This has been a great deep dive, everyone. Thanks for joining us.